This video will introduce students to the IC555 timer. This video also shows the operation and application of 555 timer work in Astable mode.
Assalamu alaikum and hi everyone. Today we are going to learn about very useful IC, the 555 timer, and how it work in Astable mode. The 555 timer, designed by Hans Commonzind in 1971, can be found in many electronic devices starting from toys and kitchen appliances to even a spacecraft. It is a highly stable integrated circuit that can produce accurate time delays and oscillations. The 555 timer has three operating modes: bistable, monostable and Astable mode. The 555 timer is probably most common and popular IC to be used in hobby circuit. It's easy to find a schematic to make a project, but to better know how it work in circuit, I want to talk what happening inside the 555. The 555 timer is a switching circuit contain the 8-pin IC. They can act like timer, oscillator or flip-flop. Let's take a look. 8-pin. As usual, we can find pin 1 to the left north or dot.
Pin 1 ground. Pin 2 trigger input. Pin 3 output. Pin 4 reset. Pin 5 control voltage. Pin 6 threshold. Pin 7 discharge. Pin 8 power supply. How it works: internal schematic and block diagram. Let's take a closer look what's inside the 555 timer and explain how it works in each of the three modes. Here's the internal schematics of 555 timer, which consists of 25 transistors, 2 diodes and 15 resistors. It is represented with a block diagram. It consists of 2 comparators, a flip-flop, a voltage divider, a discharge transistor and an output stage. The voltage divider consists of 3 identical 5K resistors which create 2 reference voltages at 1/3 and 2/3 of the supplied voltage, which can range from 5 to 15 volts. Next, there are the 2 comparators inside the 555 timer. A comparator actually is a circuit element that compares 2 analog input voltages at its positive, non-inverting, and negative, inverting, input terminal. If the input voltage at the positive terminal is higher than the input voltage at the negative terminal, the comparator will output 1. Vice versa, if the voltage at the negative input terminal is higher than the voltage at the positive terminal, the comparator will output 0. The first comparator negative input terminal is connected to the 2/3 reference voltage at the voltage divider and the external, control, pin, while the positive input terminal to the external, threshold, pin. The second comparator negative input terminal is connected to the trigger, pin, while the positive input terminal to the 1/3 reference voltage at the voltage divider. So using the 3 pins, trigger, threshold and control, we can control the output of the 2 comparators, which are then fed to the R and S inputs of the flip-flop. The flip-flop will output 1 when R is 0 and S is 1, and vice versa, it will output 0 when R is 1 and S is 0. Additionally, the flip-flop can be reset via the external pin called reset, which can override the 2 inputs, thus reset the entire timer at any time. The Q-bar output of the flip-flip goes to the output stage or the output drivers, which can either source or sink a current of 200 mA to the load. The output of the flip-flip is also connected to a transistor that connects the discharge pin to ground. Next, let's see how the 555 timer works in an Astable mode. In this mode, the IC becomes an oscillator, or also called free-running multi-vibrator. It doesn't have a stable state and continuously switches between high and low without application of any external trigger. Here's an example circuit of the 555 timer operating in Astable mode. We only need 2 resistors and a capacitor. The trigger and threshold pins are connected to each other, so there is no need of external trigger pulse. Initially, the voltage source will start charging the capacitor through the resistors R1 and R2, while charging the trigger comparator will output 1 because the input voltage at the trigger pin is still lower than 1/3 of the supplied voltage. That means that the Q-bar output is 0 and the discharge transistor is closed. At this time, the output of the 555 timer is high. Once the voltage across the capacitor reaches 1/3 of the supplied voltage, the trigger comparator will output 0, but at this point that won't do any change as both R and S inputs of the flip-flop are 0. So the voltage across the capacitor will keep rising, and once it reaches 2/3 of the supplied voltage, the threshold comparator will output 1 to the R input of the flip-flop. this will activate the discharging transistor, and now the capacitor will start discharging through the resistor R2 and the discharging transistor. At this moment the output of the 555 timer is low. While discharging, the voltage across the capacitor starts to decline, and the threshold comparator right away starts to output 0, which actually doesn't do any change as now both R and S inputs of the flip-flop are 0. But once the voltage across the capacitor drops to 1/3 of the supplied voltage, the trigger comparator will output 1. This will turn off the discharge transistor and the capacitor will start to charge again. So this processes of charging and discharging between 2/3 and 1/3 of the supplied voltage will keep running on its own, thus producing a square wave on the 555 timer output. We can calculate the time the output is high and low using the shown formulas. The high time depends on the resistance of both R1 and R2, as well as the capacitance of the capacitor. On the other hand, the low time depends only on the resistance of R2 and the capacitance of the capacitor. If we sum the high and low times we will get the period of 1 cycle. On the other hand, the frequency is how many times this happens in 1 second, so 1 over the period will give you the frequency of the square wave output. Waveform of the 555 Astable. Equations for Astable circuit. Applications of 555 Astable.
555 timer project can be used to test the operation of servo motors. It works with 6-volt servo motors, which are the common hobby type that we normally use in our projects. It has 2 buttons, one to send the servo in forward and another to send it in reverse. To build this project will require a 555 timer, 2 momentary contact normally open push button switches. We'll need 5 resistors, a 220 ohm resistor, 2 10K resistors, a 33K resistor, and a 68K resistor. We'll also require a 0.1 microfarad capacitor. I'm using a 2N2222 transistor in this design, but you can use any equivalent NPN transistor. And we'll also be powering everything with a 6-volt battery. Now here's how we're hooking up the circuit. The 555 in this mode is acting as an Astable multivibrator, whose frequency is determined by the capacitor tied to pin 2 and the resistor tied to pin 7. The pulse width is determined by the 2 different resistors tied to the push button switch, and this is why one of them will send the servo forward and the other will send it backwards. The output of the 555 is connected to the base of our transistor through a resistor because transistors are current driven. So let's hook this up and see if it'll move our servo motor. And so here's my servo motor tester circuit, and as always I've got it on a solderless breadboard. I've got my 2 push buttons which should control the direction the servo is going, and naturally I have a servo motor connected as well, and this is being powered by a 6-volt power source, which is 4 AA batteries in this particular case. And so pressing this button should move it in one direction, and pressing this one moves it in the other direction. And it seems to work very well. One thing I notice actually, compared to some Arduino circuits, is there's no chattering on the servo when it's sitting there stationary. It's just sitting there perfectly stationary doing nothing, which is actually great, and that's because of course it's not actually getting a signal right now. And so it does have an advantage over that kind of a system. And you could use something like this to actually drive a servo motor, not just test a servo motor, but of course you would need to experiment a bit with the value of resistors that were attached to the switch or whatever it was that you were using in order to drive the motor. But again, another great use for a 555 timer. In this 555 project, we're going to build a small DC motor controller. This is a unidirectional controller that has a speed control. We'll be building it using a separate motor power supply, and you can use a variety of motors and power supplies with this design. Now here are the components we're going to need to build the DC motor controller. We'll require a 555 timer and a 100K linear potentiometer. We'll also be using an IRF 520 MOSFET on the output. Now you could use a different MOSFET if you wish. We'll require a 1K resistor, 3 1N4004 or equivalent diodes, and 2 0.1 microfarad capacitors. Our circuit will be powered by a 9-volt battery. We'll be driving a small DC motor, and we'll also need a power source for our DC motor. Now here's how we'll hook up our circuit. We're using the 555 timer in an astable mode. The frequency of the output is determined by the 0.1 microfarad capacitor tied between pin 2 and ground, and the resistor tied between pin 7 and the VCC. The pulse width is dependent upon the position of the potentiometer, with the two diodes modifying the pulse. The output on pin 3 is fed to the gate of our MOSFET. The MOSFET then drives our motor, and note that we have a diode across the motor that protects from any back EMF that may be generated by the motor. So let's hook this up and see how it can control our DC motor. So here's my motor controller wired up onto a solderless breadboard as usual, and you can see over here I've got my potentiometer, which is my speed control. Here is the MOSFET, the power MOSFET that is going to drive the motor, and over here is my fan, and my fan is mounted on a little piece of perf board. This is something you may have seen before. I've used it in previous videos, and it's just one of the things I use for prototyping, so I find this very easy to use whenever I'm trying to test out a motor. Now this motor runs on 6 volts, so as you can see over here I've got 4 AA batteries powering it, and I've got a 9-volt battery powering the motor driver itself. And so I'm going to just turn the speed control. And there we are at full speed, and we can reduce the speed. Bring it lower if we wish. Bring it quite low if we want to. And so we get a nice control over the speed. And of course we've seen Arduino designs that use pulse width modulation that do the same thing. But once again, I want you to bear in mind the cost of the devices over here. We're using essentially the same MOSFET that we would use with an Arduino based design, but we're using a very inexpensive 555 timer chip. And so this is a much cheaper design than an Arduino based design, and if all you want to do is control the speed of a DC motor, this will work great. Now you could choose a different MOSFET if you wanted to. This one has a reasonable rating on it, but you could get one that's rated at a higher current to drive a much bigger motor. This MOSFET also is rated for a much higher voltage, so you certainly don't need to restrict yourself to just a 6-volt motor. You could do a 12-volt or even a 24-volt one with this. And so it's quite a versatile design. So if you're looking for a PWM motor control and you don't need direction control, you might want to consider using a 555 timer instead of a microcontroller.